Um, in this lesson, we're also going to be introducing the concept of function. Functions are pretty important. They are one of the most important concepts in all of mathematics, after the concept of number and the concept of set. The concept of function is probably the most important concept in all of math. So we're going to be using functions from now on, basically always, like in every math course that you have to take. And for the rest of the semester, now we're going to be talking about functions. Computers also use functions all the time to perform many of their tasks. And if you ever uh, learn computer programming, you will be using functions to tell the computer what to do. So what is a function then? A function, um, in order to define a function, you need two sets: a set A, which we're going to call the domain, and a set B that we're going to call the codomain. Once you have the two sets, a function from a set A, so let's say this is A, to a set B is just going to be a rule of assignment, right? Is a rule that tells you how to associate an element in B for each element in A. So for each element in A, you're going to associate something in B. And that could be represented like by a diagram like this. Let's say for this point right here, I can associate this point right there. And then to this point, I can associate, let's say, this one. And to this point, and I can associate, let's say, that one. And to this one, let's say I'm going to associate this one. Okay, so that's my rule. This is my made-up example. That's my rule. This is my rule of assignment. So that's what a function is. It's a rule of assignment, but there's got to be some other conditions too that I haven't mentioned yet. But besides being a rule of assignment, which, by the way, the book calls it a correspondence. So in my math lab, you're going to see the word correspondence, which is the same as the rule of assignment. So it is a rule of assignment that satisfies one more thing. For each element in A, you have to associate an element in B, right? But the condition is that the element, you can only associate one element in B. So for each element in A, you have to associate an element in B and no more than one element in B. So one and only one. So for each element in A, there exists one and only one, no more than one element in B associated to that. So basically, in terms of diagram, means that for each point here, for each element in A, there has to be an arrow emanating from that point and landing somewhere in B, but there cannot be more than one arrow. So it has to be one arrow and no more than one arrow. So that means that you cannot have something like this. So you could have that, 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 and that. Okay, so this is bad because there's two arrows coming out of the same dot, right? So that means this element would have two associated elements in B, and that cannot happen. It has to be one and only one. So for each element here, there has to be an arrow coming out of there, but no more than one arrow. There has to be one and only one arrow coming out of it. So that's fine. Sorry, that's wrong. You cannot have that. You could have two arrows landing in the same spot. So you could have this, So let's say these two are associated to that one, and that one to that one. You could have two arrows landing in the same spot. That's fine, but you cannot have two arrows emanating from the same spot. So in other words, this is not allowed. So this is a no, but this is fine. You could have two different points landing on the same spot. That is okay. And also note that you always have to use every element in A. From every point in A, there has to be an arrow coming out of there and landing somewhere in B. But it could happen that you don't always use all the elements in B, right? There can be leftovers in B, but they cannot be leftovers in A. Every element in A has to be used. Not every element in B needs to be used, right? There could be leftovers in B, so that's okay as well. All right, so that is what a function is. It's a rule of assignment that for each element in A, there is an associate element in B and no more than one associated element in B. Okay, with that said, let's look at these diagrams and figure out whether each of these rules of assignment or correspondences are functions. So let me zoom in here a little bit. Okay, let's look at this one. Right, that's my set A and that's my set B. Do you think that is a function? If you answered yes, then you are correct. This one is a function. It is a function. For each element in A, there is an associated element in B, right? For each element in A, there's an arrow coming out of it, and there's no more than one arrow coming out of it. As I told you, you could have two arrows landing on the same spot, that's fine, but you could not have two arrows coming out of the same element in A. So that satisfies the definition of function. Moreover, you see there's no leftovers in A. Every element has something coming out of it, has an arrow coming out of it, so it is a function. Okay, how about to the next one? Look at this one. Is that a function? Is that a function? So this one, the answer is no. And what ruins it is this thing right here. A, right? There are two arrows coming out of A. That is not allowed. You cannot have that. You cannot have two arrows coming out of an element. So that's not a function because of that. Okay, now let's look at C. Is that a function, yes or no? This one is a no because not every element in A was used. It is okay not to use elements in B, but it is not okay to leave elements in A stranded like that. So that is bad. You have to have something assigned to B. So that's what ruins this one. That's not a function. Okay, how about this one right here? Is that a function, yes or no? This one is a function. Yes, this one is a function. For each element in the first set A, there is an element in B. And there's no more than two arrows coming out of element in A. There's one left over in B, but that's okay. So that one is a function. Okay, now let's look at the next 6. Is that a function? Okay, so all of these don't have the same label, but the first one is a set A. This other one is a set B. Okay, is that a function? Yes or no? That one is not a function. Again, for the same reason that this one is not a function. It has an element that is not being used. It has nothing assigned to it in B. So there's an element in A that it has nothing assigned to it in B. So that cannot happen. All right, how about the next one? Is this a function? Yes or no? That one is a yes, right? There's nothing wrong with it. You could have two different elements landing on the same spot, that's fine. How about that one? C? The function, yes or no? Oh, by the way, I said no for this one and I didn't write it down. That one was a no. Okay, how about the next one? Is this a function? Yes or no? That one, the answer is no. Right, there's two violations here. There's two arrows coming out of 2, and that would have been enough to make it not a function. And there's also 2 arrows coming out of 3. So that is a no. Okay, here's 3 more. Is that a function? Yes or no? If you said no, then you have it right. It is a no because there's a violation right here. You cannot have 2 arrows coming out of 5. That ruins that. You could have 2 arrows landing in the same spot. Again, that's fine. But this one is not. Okay, how about that one? E. Is that a function? Yes or no? This one is a yes. Okay, every part of the definition of the function is satisfied. Every element in A has something associated in the set B, and for each element in A, there's one and only one element to be associated to it, right? There's no 2 arrows coming out of an element in A, and no element in A is left out. Every element is used, right? There's an arrow coming out of every element in A. So that's a yes. And last one, is this one a function? Yes or no? If you said no, that's correct. Because there's no assignment, right? No element in this set has anything assigned to it in the other set. There's no rule of assignment to begin with. There's 2 sets, but there's no rule of assignment. There's no arrows at all, so that's not a function. Okay, there's a very common notation that we use for functions. We sometimes, we often give a variable name to a function. It is very common to use f for function, but also common are other letters as well, such as G, H. These are the most common ones. I mean, we can use any letter of the alphabet for a function, and even letters of the Greek alphabet, but F is a common one. So we're going to say that the rule of assignment is F from A to B, and this is the way we write it. f goes from A to B. F goes from A to B. So sometimes we write it like this. If you have, that's your function, we say f, we go from A to B, and we write it like this as well. The function f goes from A to B. Alright. And one thing to note, though, is that not every function can be represented in terms of diagrams. Not every function can be represented in terms of diagrams because it could happen. One reason, for example, is that the domain is too large, right? If there's like 7 million elements in A, that would be impossible to make a diagram for that. It would be too large. You cannot make a diagram for that. Okay. There's also a little bit more vocabulary. The elements in A are called the input, the inputs. Remember that the set A is called the domain, but the actual elements inside A are called inputs. And the corresponding associated element to it in the codomain, remember the set B is called the codomain, the corresponding element associated to an input is called an output. And we use this notation. F of A equals B. If A is the input and B is the output, and F is the rule of assignment, and A is associated to B, by means of that rule of assignment, write F of A equals B. So one last example here. Suppose that this is my set A and that's my set B, and to each element in A I associate its square. So that means 1 is associated to 1 because 1 squared is 1. 2 is associated to 4 because 2 squared is 4. 3 is associated to 9. And 4 is associated to 16. If we call this function f, right, then we can, instead of drawing a diagram, we can just say 1 is associated to 1, 2 is associated to 4, 3 is associated to 9, and 4 is associated to 16. So when the input is 1, the output is 1. When the input is 2, the output is 4. When the input is 3, the output is 9. When the input is 4, the output is 16. So that's a more convenient notation that we use for functions. And we say, when we're evaluating the function, we sometimes say that we're plugging in the input. So if this is my function, then when I plug in 1, I get 1. When I plug in 2, I get 4. When I plug in 3, I get 9. And when I plug in 4, I get 16. One other way to indicate the rule of assignment of a function is by means of a table of values, which is similar to the idea of a diagram, but it's just in the form of a table. And again, that is only possible when the domain is not too huge, right? If the domain is 2 billion, then a table that has 2 billion rows is kind of hard to read. So when the domain is not too large, that could be a convenient way of writing the domain, an alternative way, a different way of expressing the function. So here's an example. Let's look at this example and determine whether the following rules of assignment are functions. Remember that where you're going to see in the homework is correspondence. Determine whether following correspondences are functions. So here's the first one, the first table. Is that a function? Yes or no? So this one should be a yes to every element in A, the inputs, varies as an associated output, and there's no input that has two different outputs. So this is a yes, this is a function. How about the next one? Is this a function, yes or no? This one is actually not a function. Can you tell why? The element -8, you see that has two associated outputs. -8 is associated to 5, and then down below they tell me -8 is associated to 0 as well. That doesn't work. That's not a function. An input cannot have two different outputs. This is a no. That's not a function. How about the last one? Is that a function? Yes or no? This one is a yes. Every input has an associated output, and no input has two different outputs. Okay, another way of expressing a rule of assignment besides diagrams and besides tables is using words, right? You can use words to describe the process of assignment, to describe how an input is associated to an output. So let's look at these examples and determine whether they are functions or not. The first one says, suppose that the set A are students at CCGA and the set B are 10-digit numbers, which are basically going to be ID numbers, 10-digit numbers. And suppose the rule of assignment is that to each student, I associate his or her CCG ID number. That's the rule. To each student, I associate is CCG ID number. So I input, let's say this is a computer, I input the student's name, and the computer is gonna give me as an output the CCG ID number. Is that a function, yes or no? If you said yes, then you are correct. This is a function because each student, once they're admitted to CCGA, right, they are assigned a CCGA ID number. So each student is going to have an ID number, and no student has two ID numbers. That means there wouldn't be two, if we made the diagram for this, there wouldn't be two arrows coming one of one student. So each student has one and only one uh, assigned ID number. So that's a function. How about the next one? Let's suppose that A is a set of all books in a library. The set of all books in a library. Imagine it's a big library, a specific library. And B is a set of all book authors. So it's names of people that have written a book, book authors. And suppose the rule of assignment is that to each book, you associate the book's author. It's that correspondence a function. The answer to this one is no, because one book could have more than one author. One book, or a book, which is the input, could have more than one author, which are the output. So one input could have more than one output, and that's not allowed. And it's very easy to find a book that has more than one author. So that's not a function. All right. Finally, well, there's two more ways of describing functions. Besides, so now we have diagrams, tables, words. Another way of representing functions is by means of using formulas or equations. This is a pretty popular way representing functions. One that, I mean, not popular, but like it's used a lot. Is a very common way of encountering functions by means of formulas or equations. So, for example, you could have a formula like this: function going from all the real numbers to all the real numbers, and the rule of assignment is to each input I add 1, and that's my output. So if you give me 5 as an input, the output would be 6, because I just add 1 to it. And that description right there perfectly describes a function. All right. Now, evaluating a function when you have a formula is very easy. In the case of a diagram, it's a matter of chasing the arrows. In the case of a table, it's just looking at the output. But if you have a formula, that's also very easy. It's a matter of plugging in. So if I give you, look at this example. Suppose I give you a function, the function being f of x equals x cubed plus 5x, and ask you to find what are the outputs when the inputs are -1, 0, and 2. Or in other words, find f of -1, f of 0, and f of 2. All you have to do is plug that in, plug those numbers in. So for example, to figure out what is f of -1, we plug in -1 in here, in the formula. So this is going to be, instead of x, I write -1. So -1 cubed plus 5 times -1. -1 cubed is -1. 5 times -1 is -5. So the answer is -6. The output when the input is -1 is -6. To find the output when the input is 0, just plug in 0 in the formula. So that means this is 0 cubed plus 5 times 0, which is 0, plus 0, which is 0. And finally, what is the output when the input is 2? In the formula, I replace x with 2, so this will be 2 cubed plus 5 times 2, which 2 cubed is 8, so 8. 5 times 2 is 10, so this is 18. And that's how you evaluate functions when you have the formula. You just plug it in and simplify. Lastly, the last way of representing a function could be by using graphs. So that means we have how many ways? Diagrams, tables, words, formulas or equations, and graphs. So we have 5 ways of representing a function. The last one is in terms of graphs. Now, if you take the definition of a function and you interpret it in terms of graphs, there's a very easy way of determining by just looking at it if that thing that we're looking at, whether it's a function or not. In the case of diagrams, you just look at the arrows and see what they're doing. In the case of a graph, all you have to do is apply the so-called vertical line test. So if you have a graph of something, you're going to be able to tell whether that is the graph of a function or not by just applying this test that says no vertical line whatsoever is going to intersect the graph more than once. If no vertical line intersects the graph more than once, then that is indeed the graph of a function. What you have in front of you is a function. Okay, so let's look at some examples. Here's this one. Yeah. So let's look at each of these ones and just check off whether they're functions or not. So here's the first one. Is that a function? The graph, if you cannot see that very clearly, the graph is uh, that's horizontal straight line. That's the graph. Is that a function? Yes or no? So that is a function because if you imagine vertical lines, there's no vertical line that intersects that horizontal line more than once. There's no vertical line that is going to cross that horizontal line more than once. So that is a function, is a graph of a function. Okay, how about the next one? This one. Is that the graph of a function, yes or no? That one is no, right? Because I can easily just draw a line, a vertical line, that touches the graph more than once. Graph, it crosses it there, and it crosses there. And there's not necessarily a unique vertical line. I could have drawn basically any vertical line in there, and it would have crossed the graph more than once. That's not allowed. That's not a function. What that says is that this input has two different outputs. The input when x equals 2, sorry, that's a 1. When x equals 1 has two different outputs. Namely, the output -2 and the output 2. That's not a function. How about this one? Is that the graph of a function, yes or no? That one is a yes, because if you imagine vertical lines, there's no vertical line that is gonna intersect this graph at more than one point. That is a function. So this is a function. How about this one? The graph of that one is not very clear, but this is like a trapezoid. So this is the graph. You have that, 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 that. Okay, so that's my graph. Is that the graph of a function? Yes or no? That one is a no, because you could easily draw a vertical line that intersects this graph at more than one point. So this is just one example. That's one. There's many more, right? You could draw anywhere here. All those vertical lines intersect the graph more than once, so that is not a function. How about this one? Is that a function? Yes or no? This one should be yes. Now that looks a little bit fuzzy here, it's blurry, but this section right here is supposed to be like this one. Uh, really shouldn't, it really is not intersecting. There's no vertical line that intersects at more than one point. This one is a square. That one is like the trapezoid. This one is not a function. Because, for example, that vertical line right there intersects it at those 2 points. So this is not a function. How about these last three? 7, 8, or 9. Is that the graph of a function? That one is a yes. There's no vertical line that intersects that line more than once. This one, yes or no? This one is a no. You can easily draw a vertical line that crosses that graph more than once. That's a no, not a function. It's not the graph of a function. And the last one, is that the graph of a function, yes or no? Let me make it darker. Yeah. So you have that. Okay. Imagine vertical lines. There's no vertical line that is going to cross that graph more than once. There's none. So that means this is a function.